All right, notes 11.7, the basics of probability. So we're going to start talking about probability today. We'll break this section into two parts, so 11.7.1 homework and 11.7.2 homework. All right, let's start with some terminology. The set of all possible outcomes for an experiment, for example, tossing a coin or rolling a die, for example, is referred to as the sample space, and it's denoted with a capital S. In this section, we will assume that all outcomes are equally likely. So when we're talking about these stuff here, we're going to get later on, we're going to get outcomes that aren't equally likely. But for now, we're going to assume that all outcomes are equally likely. So for example, I'm going to toss a coin or roll a die, and we're going to assume that those are fair. So the die isn't weighted in some way so that a 6 is more likely to come up than normal. So each outcome will be equally likely. The experiments will be considered fair. All right, so some examples. If we toss a coin, the sample space S, we're using set notation here. So the sample space contains two outcomes, a heads or a tails. Rolling a die, the sample space has 6 outcomes, 1, 2, 3, 4, 5, or a 6, assuming we have a standard die. All right, choices on a multiple choice test question. The sample space A, B, C, D, E. Again, you know, your science teacher may tend to put more B's on than anything else on a test, but again, we're going to assume they're all equally likely. And then tossing 2 coins. Well, if we toss 2 coins, if the experiment is actually tossing 2 coins, then there are only 4 outcomes that are possible. So both are heads. We have a heads to tails, we have a tails to heads, or we have 2 tails. Again, all equally likely, so we're listing them in this way. So notice the use of set notation, and that for each experiment, each outcome in the sample space is equally likely to occur. Now again, that's not always the case, but in the way we're presenting this first part of this section, we're going to assume that. So a subset. A subset of a sample space is just referred to as an event. So for example, getting an even number could be considered an event. And so we would say, in this case, let's call it E for event with the subscript of 1, because we may have more than one event. So we're going to call the first one E sub 1. And that would involve, instead of a 1, 2, 3, 4, 5, 6, if we're talking about the event being an even number, 2, 4, and 6. Getting 2 heads when tossing 2 coins, we could call this event 2. So event 2, using set notation, would be HH. All right, we'll represent the number of outcomes for a particular event using this notation. So like it's a function, the number of outcomes that would satisfy a particular event. So it's like f of x, in this case, n of e. So that in our examples that we use up above, the number of outcomes in event 1, the number of ways of getting an even number on a die would simply be 3. And the number of outcomes for event 2, that was getting 2 heads, would just be, I guess there should be an n here. The n of getting 2 heads is just 1. There's one way of getting 2 heads when tossing 2 coins. All right, so probabilities. The probabilities then is simply the number of successful outcomes divided by the number of outcomes in the sample space, right? So the number of successful outcomes for a particular event divided by the number of outcomes in the sample space is going to be our probability of that event happening. All right, so let's look at some examples. So example 1, a single die is rolled. Write each event in set notation, find the probability of the event. All right, so E sub 1. So E sub 1, and then use set notation. It is the number showing is a multiple of 3 when rolling a die. So that's going to be 3 and a 6. All right. So what is the probability of event E1 occurring? All right. So there are two outcomes divided by, if you remember up here, there are clearly 6 outcomes that are possible. So 1/3 is the probability of rolling a die and getting a number that is a multiple of 3. All right, B, event 2, the number showing is less than 6. All right, so this is going to be 1, 2, 3, 4, 5. The probability of event 2 happening is clearly the number of outcomes, 5, over the total number possible in the sample space, 6. All right, C, event E3. The number showing is a 7. All right, so how many ways can that happen? What are the possible outcomes? Well, we're going to leave it as an empty set. We could have also have done it as the null set. Remember, don't put the null set in the empty set. That would not make any sense. All right, and so then the probability of event 3 happening is there's 0 ways that can happen, over 6 total ways, or simply 0, because obviously a standard die does not have a 7 on it, so it's not possible. All right, so event 4, the number on the die shows a number greater than 0. Well, that's simply the whole entire sample space. Every outcome would satisfy that. Okay, so the probability of event 4 happening is 6 over 6, or 1. There's no way this can't happen. It has to happen. It's a certainty to occur, so it's a 1. So that kind of gives us some of the basic probability rules here. An event that is certain to occur, like the last one we just did, clearly has a probability of 1. The probability of an impossible event, like getting a 7 on a standard die, that's 0. And so the probability of any event must be greater than or equal to 0, less than or equal to 1. So the probability of any event is between 0 and 1 inclusive. All right, so complements now. The basic idea of complement. So the set of all outcomes in a sample space that do not belong to event E are basically known, is basically known as the complement of E. And so we'll denote complement of E as E with a little apostrophe, or we'll call that E prime. So if E is the event of drawing a jack from a standard deck of cards when drawing one card, then E prime, or the complement of E, is the event of drawing some card other than a jack. In this case, note the number of outcomes for E is 4. There are 4 jacks in a deck. We'll see that in a second on the next page here. And the number of ways of the complement of E happening, not getting a jack, well, that would be 48. Don't really need those numbers here, but just we'll see that more when we ask to find some probabilities. All right, so the event E union the complement of E, together those make up just the sample space. If we want to look at continuing sort of with our set notation here, the E and the complement of E, so that what values are in both of those? Well, there are no values that are both in E. So in other words, when I pull a jack from a deck, a card from a deck of cards, the event that it's a jack would be either a jack, right? And then not a jack, right, would be some other card other than a jack. So the intersection of those two events, can the card be both a jack and not a jack? And so the answer is no, they can't both happen at the same time. because they're complements of each other. So that would be it's not possible, right? There's nothing in that set. The intersection of E and the complement of E is the empty set or the null set. All right, so now let's think about some probabilities. The probability of getting a jack plus the probability of not getting a jack will clearly be 1, right? Those are all the possibilities. Essentially, what's the probability of getting something out of the sample space? Well, that's got to be 1, right? So another way of taking it, if we take this equation and rewrite it a little bit, we could find the probability of an event by taking the probability of its complement and subtracting it from 1. So sometimes rather than finding the probability of an event directly, it's easier to find the probability of its complement and then subtract that from 1. So this Venn diagram kind of demonstrates the idea here. These are not overlapping events, right? So this is sample space S, and we're either E or we're not E, right? The complement of E or E prime. There is no overlap between the two, all right? All right, let's go on to page 2. All right, the beginning of page 2 is showing us a standard deck of cards. So a lot of the stuff we do is going to be involving a standard deck of cards. So if you're not comfortable with what the makeup of a standard deck of cards is, I've got it here on our notes. Notice there are 4 suits. There are clubs, in no particular order here. Clubs, spades, hearts, and diamonds. Notice there are no ones. There's aces. And then 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's jacks, there's queens, and there's kings. These are considered face cards. Now sometimes a 10, a jack, a queen, and a king might have the same value depending on what card game you're playing. But 10s are not face cards. Also, students often think of aces as face cards. There's no face on an ace. So, the face cards are so called because they have faces on them. So these are the only face cards. So there are 12 face cards out of a deck of 52 standard cards. When we talk about standard deck of cards in this class, we will not be considering jokers. So make sure that if we're talking about a standard deck of cards, we're talking about 52 cards. All right. I guess that's all that we need to know about the standard deck of cards. All right, so let's go to example 2. Drawing a card from a standard deck. Let E be the event of drawing a heart. So find the probability of E getting a heart. So you could say probability of E. Sometimes we'll use symbols like probability of a heart, whatever you want to do. So the probability of getting a heart. Well, how many hearts are there? Well, 1/4 of the deck is hearts, right? So we could, probably just jump to 1/4. Or we could say, well, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. That's 13 out of 52. Of course, we'll always reduce our answers. But we already know that 1/4 of the cards are hearts anyway. So we could have just jumped to 1/4. But there are 13 successful outcomes, which are a card that's a heart, out of the 52 cards in the sample space. All right, the probability of not getting a heart. All right, so the probability of E prime, that's going to be all of the other cards. So we could just say the complement of, so in other words, we could say 1 minus the probability of an E, right, using our complement rule. And so that's just 1 minus 1/4, or clearly 3/4 of the cards, right? 1, 2, 3 of the 4 rows are not hearts. Okay. All right, drawing a card from a standard deck, let E be the event of drawing an ace. All right, so an ace, so that's this, right? So the probability, and if you want to just say something like probability of A for ace, that's fine. Or if you want to use the E, that's fine too. So the probability of an ace, well, there are 4 aces out of the 52 cards total. Of course, we reduce that fraction. So there's a 1 in 13 chance, or probability of 1/13 of getting an ace. So what's the probability of not getting an ace? I'm going to go with E prime in this case. So probably of not getting an ace. So we could count up all the cards that are not aces. Well, that's 48, and divide that by 52. But we could also say, well, that's 1 minus 4 out of 52. Or we could say that's 1 minus 1/13, or clearly 12/13. Either way you get to it, eventually you should get our reduced fraction that looks like this. Okay. All right, now we're going to talk about something that's related to probabilities. It's called odds, and we're going to develop a formula here, but let's just talk about it in example C here, example 3C. The odds of getting an ace when drawing one card is defined by the ratio of the probability of the event to the probability of its complement, or not, the event not happening. Now, you have to be careful. In the real world, people use the term odds and probabilities sometimes interchangeably. And often in movies, you'll see the term odds related to betting or horse racing, that kind of thing. And so what kind of odds will you give me is something that you sometimes hear. That is not the same thing as the odds that we're talking about here. So be careful. They're not the same thing. They're all related to probabilities and that kind of thing. But your horse racing, the odds that you get basically tell you how much money you're going to win if your horse comes in. But it's really based more on how many other people bet on the horse. If you're the only person betting on the horse, then your odds are going to be much higher. You're going to win more money than if everyone bets on it. Then you're going to get maybe 1-to-1 odds or something like that. All right, but that's totally different than this. So here, and to denote the difference, it's a ratio, but we'll sort of more do it as the probability of E, and then we'll do colons to do more of a ratio, to denote that it is an odds, rather than, say, a fraction, which is still a ratio, but we sort of write it in different ways. So here, we'll, if it's a probability, we'll typically write it as a fraction. If it's odds, we'll write it as like a ratio with colon between the two. So find the odds of getting an ace. So the probability of getting an ace was 1 out of 13. And then the probability of not getting an ace is 12 out of 13. And so, we know that those 13s are going to, the 13s are going to cancel. And so the odds of getting an ace, is 1 out of 12. But again, that kind of makes it look like it's a probability, because we wrote it as a fraction. So the better way of writing that is to use these colons, and so we'll say 1 to 12 odds. And so we'll write it to denote, if we see something like this, we know we're talking about an odds. If we do something like this, it looks too much like a probability, and we won't know the difference between them. So we'll make sure that we use colons to write odds. So the probability of getting an ace is 1 out of 13. The odds of getting an ace is 1 to 12. All right. So rather than the probabilities, though, we notice that the 13s canceled, right? The number of the number of possible outcomes in the sample space, which is the denominator of the top, would cancel with the denominator in the bottom, right? Those are both the number of spaces. So instead of doing the probability of the event over the probability of its complement, we can really just say the number of outcomes in the event divided by the number of outcomes in the complement. So, and then again, we'll write it in this format rather than as a fraction. We'll write it as a colon. So let's look at example 4. A marble is drawn at random from a bowl containing 6 green, 4 blue, and 8 yellow marbles. Find the odds in the favor of a yellow marble being drawn. So I'm going to think of it as how many number of ways can a yellow marble be drawn, and the number of ways that any marble in the sample space can be drawn. All right, well, no, I'm sorry, not the sample space. That would be the probability. The number of not yellow. All right, so the number of yellows is 8, divided by the number of not yellows, which is 10. All right, so what we want to do is we'll reduce this fraction. First, we'll leave it as a fraction, reduce it. So that's 4 to 5, and then we will write it as a ratio using colons. Okay, so 4 to 5 is the odds. The odds are 4 to 5. Now, you could say 8 to 10 if you wrote from here, if you wrote the odds are 8 to 10, you're less likely to reduce this and get this. So I would say is write it as a fraction, reduce the fraction, and then write it using your colon as a ratio. So we say this is 4 to 5 is the odds of drawing a yellow marble. All right, here is your homework that is due next period.